All right, gentlemen, ladies, take your seats. The door is closed. The phones are off. Today isn't about passive listening or, you know, checking your emails while something plays in the background.
Not at all.
I want you to mentally put yourself at the head of the table in a boardroom. Think Stuttgart, Detroit, maybe Yokohama.
Yeah.
You are the CTO. You are the chief architect.
You're the one on the hook.
Exactly. You are the decision maker responsible for the next generation of vehicle platforms.
Well, and we aren't just commentators today. Consider us your retained senior strategy consultants. You've brought us in because your board is, let's say, nervous.
Nervous is putting it mildly.
They see the projections. I mean, the automotive safety system market hitting, over $400 billion by 2035. They see the opportunity, but they also see the liability.
And the risk.
They see the complexity curve going vertical, and they're turning to you, and they are asking, how do we survive this?
And that liability is not just one thing. It's technical, it's financial, and frankly, it's existential. We're looking at a very specific strategic window today. The 2024 to 2026 execution phase.
The critical years.
The sources we've analyzed for this briefing, and we're talking internal white papers from ETS, architecture reports from Electrobit, global market intelligence, they all point to a singular, almost terrifying conclusion. We have hit a tipping point. The strategies that kept you safe, the ones that kept you compliant for the last 20 years, they are effectively obsolete.
Obsolete is a very polite way of putting it. I'd say they're dangerous. If you apply a 2015 safety strategy to a 2026 software-defined vehicle, you aren't just risking a recall. You are engineering a catastrophe. The core thesis of this briefing is, well, it's simple, but the execution is just brutal. The industry is moving from component compliance to system-level emergence.
Okay, let's unpack that immediately, because emergence can sound a little bit like academic fluff, but our sources suggest it's actually a hard engineering constraint.
It's pure physics.
We're seeing the shift from these distributed architectures where you had, 100 little ECUs scattered like confetti, each doing one job, to zonal and centralized compute. We're consolidating the brain of the car into one place.
Correct. And that architectural shift completely breaks the fundamental way we used to guarantee safety. We call this the shed versus skyscraper paradigm. And this is the first section of our strategic landscape assessment.
Walk us through the physics of that analogy. Why does the shift to centralized compute change the safety equation so drastically?
Okay, so think about the old world, the shed. You built a car like a simple brick structure. You bought a braking ECU from a Tier 1 supplier.
A Bosch, a Continental.
Exactly. It was ASIL D certified. You bought a steering column. ASIL D certified. Those are your bricks. And if the bricks were strong and you stacked them up correctly, the shed stood up. The integration risk was low because the complexity was contained inside the box.
So the supplier handled the internal safety, you just worried about the wiring harness.
You just worried about the harness and the power supply. The brick was a black box, and it was a safe black box. But now we're consolidating. We're taking the software out of those 100 little boxes and running it all on one massive central computer, a high-performance computer or HPC.
And that's the skyscraper.
That is the skyscraper. And you cannot build a skyscraper just by stacking strong bricks. It doesn't work. You need structural engineering.
You need a plan for how they all work together.
Precisely. The safety of a skyscraper doesn't just come from the quality of the steel beams. It comes from how those beams interact with wind loads, with gravity, with the foundation, with the damping systems. Safety becomes an emergent property. It exists only in the system context, not in the component itself.
So if I'm a director of engineering listening to this, I can no longer just point to a certificate from my supplier and say, they certified it, it's safe, not my problem.
That's exactly right. That move doesn't work anymore. In a centralized architecture, you are the architect. If the building falls down, you can't blame the steel manufacturer.
It's your design.
It's your design. You own the failure.
The sources highlight a really specific historical disaster to illustrate this point. What happens when you ignore this exact shift? The Ariane 5 rocket. Now, this isn't an automotive example, obviously, but the engineering failure is identical to what we are seeing in SDVs today.
It is the canonical case study for what we call contextual failure. Let's just look at the facts. The Ariane 5 rocket exploded about 40 seconds after launch in 1996. A total loss.
A very public, very expensive failure.
Extremely. So the investigation team, they pull the black box, they find the software that caused the crash. But here is the kicker, the part that should keep you up at night. That software had flown perfectly on the Ariane 4 for years. It was, for all intents and purposes, bug-free code.
So in our analogy, the brick was solid. It was proven in use, as the standard says.
The brick was perfect, but the context, the skyscraper, was different. The Ariane 5 had a completely different flight trajectory. It had a much higher horizontal velocity than the Ariane 4 ever did.
So the inputs changed.
The inputs changed dramatically. The software tried to convert that 64-bit floating point velocity reading into a 16-bit signed integer.
And the number was just too big to fit in the bucket.
Integer overflow. The whole inertial reference system crashed. Then, the backup system, which was running the exact same code because of a redundancy requirement, crashed milliseconds later for the exact same reason.
So the redundancy was useless.
Worse than useless, it created a common mode failure. The nozzles swiveled to their limit, aerodynamics tore the rocket apart, and it just disintegrated. $370 million vaporized. Not because of a bug, but because a team of brilliant engineers assumed proven in use meant safe in all contexts.
That is the absolute nightmare scenario for an OEM moving to a centralized architecture.
Yeah.
You take your legacy breaking code that has worked perfectly fine on a little distributed microcontroller for 10 years, you drop it onto a new high-performance computer, and you just assume it's going to work.
And that assumption, that one assumption, leads us directly to the 3 myths we need to exterminate from your engineering teams. Immediately. If we're going to be MEC mutually exclusive, collectively exhaustive, we have to clear the debris before we can build the new strategy. Myth number 1. Safety is a component property.
We just debunked that with Ariane 5. Can't buy safety off the shelf and just plug it in. What's myth number 2? This one's a favorite of middle management, I think.
Oh, absolutely. Myth 2. Safety equals passing audits.
The compliance trap.
It is the ultimate compliance trap. An audit checks your paperwork. It checks if you followed the process map you drew on the wall. It checks if you have all the signatures. It's like a driver's license.
Okay.
Having that plastic card in your wallet proves you took a test once. It does not physically prevent you from driving 100 miles per hour into a tree.
So an audit is just a lagging indicator. It tells you what you did, not what will happen.
It's worse than that. It's a procedural indicator, not a technical one. Safety is the real-world physical outcome. The audit is just the receipt for the process. You can have a perfect, beautiful audit trail and still have a fundamentally unsafe vehicle if your architectural assumptions are wrong.
Okay, that makes sense. And the third myth.
The third myth is the one that comes from the tech world, the move fast and break things world. It's the idea that safety can be retrofitted.
The we'll fix it in post mentality. I hear this all the time from software teams coming from, say, the mobile app world. Don't worry, we'll patch the safety in later.
In automotive, that is financially ruinous. It's not like a web app. If you find a fundamental safety architecture flaw during the final validation phase, you are tearing up the foundation of the skyscraper after the windows and glass are already installed.
You're talking about a complete re-architecture late in the game. The cost would be astronomical.
Exactly. You have to left shift. Safety constraints must be in the model-based design before a single line of C++ is ever written. It has to be a foundational requirement, not a feature.
Okay, so that's the strategic landscape. We're building skyscrapers, not sheds. We can't trust old assumptions. So now let's talk about the actual materials we're building with. This report is divided into technical domains, and the first one is Section 2, the MCU strategy. This is the safe world.
This is the domain of AUTOSAR Classic, deep embedded systems. Despite all the hype about AI and centralized compute, this is still the muscle memory of the car.
Right.
The braking actuation, the steering motor control, the airbag deployment, the stuff that cannot fail. This demands ASIL D, the highest automotive safety integrity level.
But the strategy here is shifting too, right? It's not just about writing clean C code anymore. The report specifically mentions tooling, things like RTA car and this concept of confidence in use. Why is the focus shifting to the tools we use?
It's because the complexity has just exceeded human capability. Nobody hand codes assembly for a modern braking system anymore. It's impossible to manage. We use code generators, we use compilers, we use model-based design tools.
So we're abstracting away from the metal.
We are. And so ISO 26262, specifically Part 8, asks a very hard, very reasonable question. How do you know your compiler isn't adding a bug?
That's a terrifyingly valid point. If I write perfect code, but the compiler optimizes it incorrectly, I have a bug I can't even see in my source file.
Precisely. You can't debug it because it's not there. So we are now forced to audit the robot that builds the robot. You need a qualified toolchain.
What does that mean in practice, qualified?
It means if The tool, the compiler, the linker, the code generator is certified by an authority like TUV-SUD. You get a kind of credit. You are allowed to trust its output. However, and this is the part where technical directors get into serious trouble, that certification comes with enormous strings attached.
The safety manual.
The safety manual. It is not a suggestion. It is not a helpful guide. It is a legally binding operating instruction for that piece of software.
And this introduces that concept you mentioned earlier, SEOC.
Yes. COOC safety element out of context. This is the industry's attempt to solve the Ariane 5 problem we just talked about.
So how does it work?
Well, think about a supplier, say Bosch or Continental. They build a generic ESP, an electronic stability program unit. They don't know if you're putting it in a heavy truck or a lightweight sports car. The context is unknown to them.
So they develop it as a safety element out of context.
Correct. And to do that, they have to define with excruciating detail the assumptions of use, or AOUs.
This sounds like where the friction really happens, between the OEM and the supplier.
Yeah.
Can you give me a concrete example of a valid assumption of use versus a bad one that you see in the wild?
Absolutely. A bad AOU is qualitative. It's vague. Something like, the integrator must ensure the power supply is stable.
That means nothing.
It means absolutely nothing. What is stable? Is a 1-volt drop over 10 seconds stable? Is a microsecond-long spike stable? It's completely open to interpretation.
It means it's open to lawsuits.
Exactly. A valid AOU is quantitative and measurable. It would say something like, the integrator must ensure the input voltage remains between 11.5 and 14.5 volts with a maximum peak-to-peak ripple of less than 50 millivolts.
Because if I, the OEM integrator, provide 11 volts and the brakes fail, it's my fault. I violated the assumption.
It's your fault.
But if I provide a perfect 12 volts and they fail, it's the supplier's fault.
Precisely. It defines the liability boundary with mathematical precision. And this discipline has to flow down into your own requirements engineering. The sources are incredibly critical of vague requirements. You cannot test a requirement like the system brakes safely.
It's not a testable statement.
It's not, but you can test the system generates 50 bar of hydraulic pressure within 200 milliseconds of receiving the brake signal. That you can measure.
So the strategy for the MCU world, the deep embedded world, is rigidity. It's a strict V model, strict traceability from every requirement down to every line of generated code, and a strict adherence to the manual.
It's unsexy, but it's the foundation of the entire car's safety.
Right. But now we have to cross the bridge. We have to go from that rigid deterministic world into the chaos. Section 3 of the report. The HPC strategy.
This is the conflict that is defining this decade of automotive engineering. It's the central tension. You need the high-performance computing, the HPC, for all the value-add features the market demands, the beautiful AI, the rich visualizations, the over-the-air updates, the connectivity.
And that means you need a real operating system. You need something like Linux.
You need Linux, but Linux is this incredible, massive open-source project with thousands of contributors all over the world. It is the absolute antithesis of an ISO 60262 development process.
So you have a fundamental collision. You have an OS that runs the world's servers and clouds, but has no single safety manager or process owner, and you're trying to put it in a car that can kill people.
A massive collision.
The report lists a few failed strategies that companies keep trying. Let's knock these down so our listeners don't waste millions of dollars in budget on them.
Yes, please. The first and maybe the most arrogant failed strategy is what we call full project qualification. This is where an OEM engineering team thinks, you know what? We will just take the Linux kernel, all 20 million lines of code, and we will reverse engineer the safety documentation for it. We will prove it is safe.
That sounds like a budget black hole, just an endless pit of money and engineers.
It's worse than that. It's impossible. You'd finish the documentation 10 years after the car launched, and by then the kernel is hopelessly obsolete. So that's a non-starter.
Okay, what's the second failed strategy?
The second one is snapshot certification. This one sounds a little more logical on the surface. You take a specific version of Linux, say kernel 5.10 enter, you freeze it, and you spend a massive amount of effort to certify that one frozen block.
That does sound logical. You treat it like a fixed component. Why is that a failure?
Because software rots. The moment you freeze it, you are vulnerable. A month later, a zero-day exploit is found in the Wi-Fi stack of that kernel. What do?
You have to patch it.
But you can't, because if you change one line of code, you break your safety certification. You are now stuck in an impossible choice. Be unsafe because you can be hacked, or be non-compliant because you applied an uncertified patch. It's a dead-end road.
So you can't certify it all, and you can't certify a snapshot. What is the solution? The report uses this brilliant analogy that I love, the trapeze artist and the safety net.
This is the only strategy we see working at scale. It's called ASIL decomposition. Here's how to think about it. Linux is your trapeze artist.
Okay.
We want the artist to do the crazy, amazing stunts, the high-end graphics, the neural network processing, the cloud connectivity. This is QM quality managed software. We don't want to restrict it with heavy safety processes. But, and this is the key, we have to acknowledge that the artist might fall.
Linux might panic. A driver might crash. It might get stuck in an infinite loop.
Exactly. So what do you do for a real trapeze artist? You place a safety net underneath. This is a separate, small, highly reliable software partition. We call it the safety monitor. It might run on a different core or in a protected memory space. Its only job is to watch the artist.
How does he watch it?
It's simple. It sends a heartbeat challenge to the Linux partition every few milliseconds. A simple, "Are you alive?" ping.
So if my infotainment system hangs while I'm doing 70 miles per hour on an ADS system like Blue Cruise,
The safety monitor detects the loss of that heartbeat from Linux. It immediately assumes the worst, bypasses the frozen Linux partition, and triggers a safe state.
and what's a safe state?
It could be anything defined in the safety plan. Maybe it engages a hardware backup path to maintain steering and keep the car in its lane. Maybe it gently applies the brakes and brings the car to a controlled stop on the shoulder. The key is that the monitor is simple enough that it can be fully certified to ASIL B or even ASIL D.
Okay, I get the analogy, but what stops the trapeze artist from falling on the net and breaking it? I mean, in software terms, if Linux goes completely rogue and starts overwriting random memory addresses, how do we protect the safety monitor itself?
Excellent question. And the answer is non-negotiable for any modern HPC architecture. You need a hypervisor.
The layer underneath the operating systems.
Exactly. A proper automotive-grade Type 1 hypervisor. The hypervisor uses the hardware memory management unit, the MMU, on the chip itself to enforce what the standard calls freedom from interference, or FFI. It builds a virtual brick wall around the safety monitor's memory and its access to critical peripherals.
A partition.
A hardware-enforced partition. Linux can crash, it can burn, it can scream, but it physically cannot touch the bits inside the monitor's protected space.
So the winning strategy is containment, not purification. We don't try to make Linux safe, we accept that it isn't, and we just make sure it can't kill us when it inevitably fails.
You've got it. We embrace the failure of the complex part, and we rely on the proven simplicity of the monitor. And the beautiful thing is, this allows your application teams to use the latest Ubuntu features, the newest AI libraries from NVIDIA, while keeping the safety engineers and the auditors happy. Because the safety net is what guarantees the life of the passenger, not Linux.
That brings us to the next layer of complexity, because this is where it gets really fuzzy. We've handled broken parts with ISO 26262, and we've just handled the unreliable OS with this decomposition strategy. But now we have AI. Section 4 of the report covers the advanced frontier, and this is where the standard 26262 really starts to fall apart completely.
It really does. ISO 26262 is fundamentally about preventing failures from internal faults. A resistor on a circuit board burns out. A cosmic ray flicks a bit in RAM. But with AI and autonomous driving, we face a terrifying new problem. The system works perfectly, the hardware is fine, the code is bug-free, and it still kills someone.
This is the domain of SOTIF, safety of the intended functionality, ISO 21448.
Right. And the classic SOTIF example is the camera system. A camera detects a shape on the road. The AI software correctly identifies that shape based on its millions of training images, but the shape happens to be a plastic bag floating in the wind, and the car slams on the brakes because it has a high probability match for a rock.
Or the reverse, which is much worse. The sun glare blinds the camera for a fraction of a second, and it completely misses the pedestrian stepping off the curb.
Exactly. The sensor worked as designed, the code executed perfectly, the car was just wrong. It reached a hazardous conclusion because of inherent functional limitations.
Now, the report mentions a new standard that's dropping right in this 2024-2026 window. ISOPUS 8800. This is specifically for AI safety.
This is the game changer. For 20 years, automotive software has been about deterministic logic. If X is greater than 5, then do Y. It's predictable. It's testable.
But AI isn't like that.
Not at all. We are moving to probabilistic logic. The AI doesn't say, that is a human. It says there is a 94% probability that the cluster of pixels designated X is a human.
So how on earth do you certify a probability? A prosecutor in a courtroom is going to have a field day with, well, we were 94% sure it wasn't a child.
You can't. So the strategy has to change. The new standard requires a concept called uncertainty quantification, or UQ. The AI system has to be introspective. It needs to know when it is confused.
So it needs a confidence score in its own prediction.
A reliable one, yes. If that confidence level drops below a certain threshold, say because of sun glare or fog or a weirdly shaped object it's never seen before, the system cannot just guess. It must be programmed to declare unknown object and trigger a fallback to a deterministic safety rule,
Like what?
like slowing the car down or widening its safety corridor, or if it's a level 3 system, initiating a safe handover back to the human driver. The point is, it has to recognize the limits of its own knowledge.
And this changes the very definition of source code, doesn't it?
Yeah.
If the behavior is learned from data, not coded in an if-then statement, what do we even audit?
We audit the data. This is a huge mental shift for engineering teams. We now talk about the data V model. Your training data set is your requirements document. It is your source code.
So if I'm an auditor coming to your company to certify your AI-based perception stack, I'm not asking to see your C++ repository on GitHub.
I mean, you might look at the neural network architecture, but primarily I'm asking to see your JPEGs, your data lake. I'm asking, show me your coverage. Do you have enough images of pedestrians in the rain at night wearing reflective Halloween costumes, in wheelchairs, prone on the ground after falling?
The long tail of edge cases.
Exactly. If your data lacks diversity, your car has a safety hole. You are no longer debugging code, you are debugging data sets.
This section of the report also highlights a really critical architectural pivot for Level 3 and Level 4 autonomy. The shift from fail-safe to fail-operational. This sounds like a massive cost driver.
It is absolutely vital, and yes, it's very expensive. Fail-safe is the standard for Level 2 systems. Think Tesla Autopilot. If the system gets confused, it beeps loudly and says, take over. It shuts down the assistance.
That's considered safe because the human is the backup.
Mm-hmm.
The human is presumed to be attentive.
Presumed. But in a true Level 3 system, like the Mercedes Drive Pilot, the driver is legally allowed to be distracted. You could be answering emails. You could be watching a movie on the center screen.
So if the system just shuts off at 100 kilometers per hour while I'm watching a film,
you die. The human takes, on average, 5 to 10 seconds to regain full situational awareness and take control. You don't have that kind of time. Therefore, the system must be fail operational.
meaning what exactly?
Meaning if the primary compute fails, if a chip overheats, if the power supply has a glitch, a secondary redundant system must immediately and seamlessly take over and continue driving. At the very least, it has to continue driving long enough to execute a safe maneuver, like pulling over to the shoulder.
That implies literally doubling your hardware cost. Redundant power supplies, redundant compute boards, redundant steering and braking actuators.
It does. It implies massive architectural redundancy. But for Level 3 and Level 4, that redundancy is the price of entry. If your business case can't support the cost of fail operational design, you can't afford to be in the L3 market, period.
Okay, let's zoom out from the silicon to the map. We are global consultants after all. Section 5 of this briefing is regional warfare. Because safety isn't being implemented the same way in Shanghai as it is in Munich or Detroit.
No, not at all. And this is causing a massive headache for global OEMs trying to build a single platform. We call it the two-speed R&D challenge.
Explain that.
You have the safety loop. This is the traditional V model world we talked about. It's slow, it's methodical, it takes 3, maybe 4 years for a major platform. Then you have the feature loop. This is the world of Agile, of CI/CD, of wanting to push updates every week to keep the customers happy with new apps and features.
And the two are in constant conflict. The safety people want to lock everything down. The feature people want to move as fast as possible.
So you have to decouple them architecturally. That's the safety island concept again. You don't update the core braking firmware over the air every Friday. That stays on the slow, deliberate, highly validated loop. You update the infotainment system and the non-critical AI models on the fast loop.
So with that in mind, let's look at the regions. Who is winning the strategy game right now?
Well, it really depends on the metric you use for winning. Let's start with China. China is, without a doubt, the speed king. The report cites Volkswagen's new CEA architecture, developed in China for China. They took it from concept to production in 18 months.
18 months. That is frighteningly fast for automotive. A normal cycle for a new EE architecture is 4 or 5 years.
It's blistering. They are aggressively decoupling hardware and software. They are focused almost entirely on one problem: city NOA navigation on autopilot in complex urban settings. They are taking calculated risks, betting that the speed of iteration will allow them to solve safety issues faster than a slow, documentation-heavy process.
Okay, so China is all about speed to market. How does that contrast with Europe?
Europe is the regulator. They are, in some ways, stifling that raw speed, but they are raising the floor for everyone. The focus is entirely on new regulations like UNES R155 for cybersecurity and R156 for software updates.
The ones that require type approval.
Yes. If you can't prove your software update process is secure and traceable, you cannot sell the car in the signatory countries, period. And then you have the consumer-driven pressure. Look at the new Euro NCAP 2026 standards.
This is where in-cabin monitoring comes in.
It's huge. The car must watch the driver. It has to detect fatigue, distraction, or even a child accidentally left in the back seat. This is becoming a non-negotiable barrier to entry for getting a 5-star safety rating.
All right, so China is speed, Europe is regulation. What about the U.S.?
The U.S. is the self-certifier. It's still a bit of a Wild West. You don't need a government agency to grant you type approval before you sell a car. You, the manufacturer, just self-certify that you meet the federal standards.
Which encourages the tech-first players.
Exactly. It encourages the tech giants, Tesla, Waymo, Cruise. They are pushing the central compute architectures the fastest because they aren't waiting for a government stamp of approval on every design change. But the flip side is that the liability risk is massive. If they get it wrong, the class action lawsuits will be historic.
But regardless of the region, every single one of these players has the billions of miles problem. You can't physically test these L4 cars enough on real roads to prove they are safe.
It's mathematically impossible. The RAND Corporation did a study on this. To prove an L4 autonomous vehicle is even marginally safer than a human driver, purely by driving, you'd need to drive hundreds of billions of miles to encounter enough statistically significant edge cases.
It would take centuries.
Literally centuries. So the only way forward is virtual validation, digital twins, running billions of miles in the simulator.
But simulations can lie. You can always program the simulation to give you the answer you want.
Which is why the real work isn't just building the simulation, it's proving it's real. You need a rigorous gap analysis. You must prove that your digital rain refracts light off the pavement in the exact same way as real rain, that your simulated tire model has the same slip angle as the physical tire. The safety argument lives or dies on the correlation between the digital twin and the physical car.
Which brings us to the final pillar of the strategy. It's the one that ties all of this together. Section 6. Cybersecurity and what the report calls continuous compliance. You mentioned R156 earlier. This introduces a specific, very bureaucratic-sounding acronym that every technical director needs to tattoo on their arm. RxSW1.
RxSWN. It stands for Regulation Software Identification Number. It sounds tedious, but it is the linchpin of continuous compliance for software-defined vehicles.
It sounds kind of like a VIN number, but for the software.
That's a great way to think about it. It's a configuration key. Think of it as a unique cryptographic hash of fingerprint of every single safety-relevant software component in the car. If you have 50 different ECUs, the specific combination of all 50 of those software versions generates one unique RxSWM.
So if I send an over-the-air update, an OTA, to just the suspension control module,
You have changed the combination. You now have a new system configuration, which means you need a new RxSWN. And you must be able to prove to regulators that this new combination has been tested and approved. You cannot just mix and match software versions in the field anymore.
this prevents what you might call Frankenstein cars, where the braking software expects to talk to version 2.0 of the steering software, but the car is actually running version 1.0 because of a partial update.
Precisely. It ensures the integrity of the whole system, but it leads to the rollback problem, which is an operational nightmare.
What's that?
Imagine this. You push a major OTA update to 1 million cars on a Tuesday morning. The update package has new software for the engine, the transmission, the brakes, and the dashboard. It successfully installs on the engine, the transmission, and the brakes. But the update to the dashboard fails because of a random memory error on that one car.
So now you have a mismatched system, an invalid RxSW configuration.
You have a potentially unsafe, uncertified car. The regulation requires that the system must be capable of an atomic rollback. It has to detect that partial failure and automatically revert all of the updated components back to the previous known good state.
If that fails, you could brick the car.
You could brick 1 million cars on a Tuesday morning. That's the kind of event that bankrupts a company. So your OTA architecture has to be just as robust as your braking architecture.
And this is why security and safety are now being co-engineered. You're using methods like STPA SafeSec to analyze how a hacker could remotely trigger a physical crash.
Correct. You can't have one team doing safety analysis in one building and another team doing security analysis in another. They're not in silos anymore. A cyber attack that disables the brakes is a safety failure. They are the same department now.
Wow. We've covered a massive amount of ground here, from integer overflows and rockets to hypervisors in Linux, from regional regulatory wars to atomic software rollbacks. As we wrap up this briefing, let's try to crystallize this. If I'm the CTO and I have my VPs of engineering in the room with me right now, what are the 4 commands I give them tomorrow morning? The top-down strategy.
Command 1, decompose. Tell them to stop trying to certify the monolithic Linux beast. It is a waste of time and it won't work. The strategy is to isolate it. Build the trapeze and the net architecture. Keep the simple, verifiable safety monitor completely separate from the complex, feature-rich OS.
Decompose. Got it. Number 2.
Command 2, shift left. Hammer this home. Safety is not a testing phase at the end of the project. It is an architectural constraint at the very beginning. If it's not in your model-based design, if it's not in your system requirements, it's not going to magically appear in the car.
Shift left. Makes sense. 3.
Command 3, quantify. Ban adjectives from requirements documents. I want you to forbid words like safe, robust, fast, or stable. I want newtons. I want milliseconds. I want degrees per second. I want probabilities. If you cannot measure it, you cannot test it, and you cannot certify it.
Quantify. No more ambiguity. And the last one.
Command 4, adapt. Embrace COOC in the safety manual. You are going to be reusing components from suppliers and from your own legacy platforms. That's fine. But you must obsess over the context. Validate the assumptions of use every single time you move a block of code to a new environment. No exceptions.
Then I'll leave you, our listener, with a final thought to chew on as you go back to your teams. We talked about ISOPA's 8800 and the shift to AI. And as we've been discussing, this isn't just a technical shift, it's a philosophical one.
It completely changes the nature of what we do as engineers.
We are moving from a world where we code rules into a machine to a world where we are trying to teach intuition to a machine. When a traditional line of C++ fails, we call it a bug. It's a defect. We can find it, we can fix the syntax. But when an AI system hits a pedestrian because it failed to recognize the shape, is that a bug?
Or is it a gap in its experience, a failure in its education?
Exactly. We are no longer debugging code. We are curating reality for a machine. And so the question for you as the leader is this. Your GitHub repo might be clean, your processes might be perfect, but is your dataset ACLD certified? Can you prove in a court of law that the data you use to teach your car covers the unending chaos of the real world?
That is the billion-dollar question. And the answer to that will determine who owns the automotive market in 2035.
Gentlemen, ladies, the briefing is concluded. Good luck with the skyscrapers.
Drive safe.